The highest point of stress in an insurance application is the moment when a user submits an unstructured, free-text damage report, and the system attempts to force that chaos into a strict, deterministic database. The Claims Enabler Mock API is a prototype designed to solve this exact stress point. Built as a local, fast API microservice, it acts as an intelligent load distributor between the front-end user and the back-end database. The incoming payload is minimal. The front end sends raw text, the SCADA text, along with an LLM temperature control, and occasionally an existing claim ID. This architecture survives unpredictable input through a state-aware triage pattern. If required data is missing from the payload, the system actively heals the gap before proceeding. This diagram outlines the full mock API. To understand how it routes data, we must trace a single HTTP request. Following the flow from left to right, we track the payload's journey from front-end transmission to a structured database output. Mapping this flow reveals how to securely embed fragile language models inside enterprise-grade microservices without compromising system stability. The payload begins its journey here, leaving the front-end request and striking the fast API gateway. A reliable enterprise system requires telemetry before any actual processing begins. That function is handled by the Lifespan Context Manager. During startup, this manager intercepts the boot process to load persistent metrics from previous sessions directly into memory. When the server eventually stops, the manager initiates a shutdown phase, safely writing those updated metrics back to the persistent store, so no telemetry is lost. The request then enters the custom middleware block. This middleware acts as a tripwire. It intercepts every single incoming HTTP request before the payload gets anywhere near the AI logic. It logs the precise execution latency, tallies the total number of requests, and tracks endpoint popularity. All of this captured data is continuously routed down into an active metrics dictionary. A dedicated metrics endpoint then exposes this dictionary, allowing administrators to monitor global API statistics. By pulling observability out into the middleware layer, the system guarantees that telemetry operations never interfere with the delicate, resource-heavy AI tasks. Once the request clears the middleware, it drops into the central logic node, the triage module. This module solves a specific structural dilemma. The downstream language models need a verified claim ID to function, but users frequently submit novel, unindexed text. The system performs an initial check against the database to verify if a claim ID already exists for the incoming request. If the database confirms the state, the yes path, the request proceeds directly to its requested endpoint for summary or classification. The critical question is how the system handles the failure state when the database returns a no. In a rigid architecture, this throws a 404 error. Here, it triggers a self-healing protocol. The triage module intercepts the payload and forcibly redirects it into a hidden, dedicated data extraction pipeline. An extraction model scans the raw text, pulling out the specific claim type, the location of the incident, damaged items, and the claimant's name. Applying a document database pattern, it immediately saves these structured data points as a standalone JSON file in the central data folder. It then generates a valid claim ID for this freshly minted record. Now the system executes a recursive step. It takes this new ID and automatically re-injects it into the user's original suspended request. State is now established. The repaired payload slides smoothly down the yes path, continuing toward the specific endpoint the client initially asked for. It acts exactly like dynamic load bearing in physical structures. If the support required to carry a load is missing, the system halts, builds the support, and then transfers the weight. This guarantees strict item potency. The front-end application receives a predictable response, completely insulated from the gaps in the back-end database. The final stage of the load path brings us to the terminal execution nodes, the 4 AI-driven endpoints. These endpoints are guarded by strict API contracts, which act as firewalls between the fast API routing logic and the language model engine itself. Pydantic schemas enforce a rigid boundary. They dictate the exact shape and type of data the AI is allowed to return. The classification endpoint, for example, is contractually obligated to return a predefined insurance category alongside a mathematical confidence score. The summary endpoint is similarly constrained, forced to distill the damage report into a strict 1 to 2 sentence reduction. This behavior is managed entirely by simple text-based base prompts, allowing administrators to adjust output parameters without altering a single line of backend code. Parallel to these operations sits a separate architectural track, the Advanced Questions endpoint. Rather than basic extraction, this node utilizes a Retrieval Augmented Generation, or RAG, architecture. It points directly at the saved JSON database files, using them as a localized knowledge base to answer natural language queries about the claims. All of these terminal nodes are currently powered by Google Gemini, routing through Llama Index, but the Fast API layer is intentionally blind to that fact. Because the contracts are strictly decoupled, the entire underlying engine could be swapped for Azure OpenAI or a hard-coded mock engine, with zero routing alterations. Zooming out, we can evaluate the completed load path from end to end. Notice the final collection point. Despite the probabilistic nature of the language models, every single execution path converges into a perfectly clean JSON output. 3 distinct layers make this possible: decoupled observability, the state-aware triage module, and strict pydantic contracts. Backed by a NoSQL document database pattern, the system executes rapid read and write cycles without stalling on schema locks. 3 text incident reports are inherently chaotic. This pipeline systematically strips away that unpredictability, yielding a deterministic API response every time. Successful integration relies on infrastructure that actively compensates for a language model's inherent volatility. Like a well-engineered physical structure, the Claims Enabler API absorbs chaotic input, routes it safely across redundancies, and delivers a stable result. This state-aware architectural design allows the system to process varying volumes of unstructured text while maintaining a consistent, structured output.